Meine Damen und Herren, willkommen zu unserer Ringvorlesung Viren und Epidemien aus Sicht der Mathematik. Dieses ist heute der zweite von 4 Vorträgen. Er wird auf Englisch gehalten. Die Ringvorlesung findet statt im Rahmen der Bürgeruniversität Frankfurt. Sie wird veranstaltet von unserem Förderverein Mathematik gemeinsam mit dem Institut für Mathematik der Goethe-Universität Frankfurt. It is a special pleasure for me to welcome our today's speaker, Professor Tom Britton. He is one of the leading experts in mathematical epidemiology. Tom Britton holds the Cramér Chair at Stockholm University, and he is currently the chairman of the Cramér Society of Sweden, the Swedish Association for Academic Statisticians. Many of you will know the name of Harald Cramér, one of the leading figures of 20th century probability. Well, it's my pleasure now to hand over to Tom, and I will stop my screen and Tom will share his screen.
The introduction, Anton, you said I was one of the world leading mathematical epidemiologists. I wouldn't say that, but I know that there is one German person who really is, or you might say was, but Klaus Dietz is a professor in mathematical epidemiology in Tübingen, by now retired, but he has done very important work in this area. So have that in mind, that Germany, you have a very strong person in this area. So my aim today is try to explain a little bit about the mathematics that you can use to derive some fairly important and enlightening results about the disease spreading. I will talk about simple models today, but there are more realistic models, but rather than showing the most realistic model with a lot of technicalities, I have chosen to use the simple models. I tend to like illustrating things with a simple model. So have that in mind, that there are more realistic models than the ones I will be talking about today. So before I go to mathematics, let's talk about reality. So here is, and what I will say today is not only applicable to COVID-19, so you should sort of think of infectious diseases in general. So here is a typical graph when you observe a new emerging outbreak. So first you have some reported cases, not very many, and then suddenly it starts to grow very, very quickly. And you might, I know that some of you know mathematics quite a bit and others less, but anyway, here this looks, it's more than linear growth, it might be exponential growth, which is very frightening because that goes very quickly. When you see a graph like this, you might ask yourself, how many will get infected? When will the peak of this epidemic be? What happens if we insert different preventive measures? Is there more data that could be collected so that we learn more about this? And more type of questions. So I will return to this type of situation, but just to let you know that this is not the only case. Another situation where you might use mathematical models is for a disease like this, and this is actually a German data. It's for a rotavirus, and the reason I have chosen German data was that I had a German PhD student, Teresa Stocks, who worked on this particular data. And here we see reported cases over time, and there is an outbreak every year, and it goes up and down. This is the reported cases, and actually the data was collected not only like this, but in 3 age cohorts, I think. Small children, adults, and elderly. So you had this type of graph for all three. But of course, not all individuals are reported, in particular the adults and elderly people. The rotavirus has very mild symptoms, so you don't observe them very much. So there are a lot of questions that you can ask. What is the average age of infection? If you start vaccinating, how many do you need to vaccinate? Another important thing is, okay, this is the reported data. Can we say anything about what fraction is not reported by just observing this? And seasonality and the other things. So a lot of questions appear for this type of problem as well. Here's another data. It's much older data. The figure here is slightly small, so I will tell you what it says. Here it is time as before. It starts with 1948 and ends with 1968. The data is reported cases and the disease is measles. And the reason why we have this old data is that it's pre-vaccine. So there was no vaccine at this period in time. This graph here is for England and Wales, and this graph here is for Iceland. So also I have been working on trying to understand this type, what is going on here, but many others, and in particular Brian Grenfell, who is professor at Princeton University, has done a lot of important work here. So one thing that is striking, just as was the case for the rotavirus, is seasonality. However, there is a big difference. Here, there is a peak. There is not a peak every year, but there is a peak every other year. So why is that? Also, if you take a closer look, it starts going up in August, September. So why could that be? Well, the simple or simplified explanation is that you start seeing a peak when children come back to schools, and this happens in early September. So then we have an outbreak, and then it goes down. But then people come to school the next year. But why is there not an outbreak then? Well, simplifying a little bit, it's only the first graders that have not experienced the disease since there was an outbreak the year before. So in the school, it's only first graders that are susceptible, the rest are immune. So that's not enough to trigger a new outbreak. Whereas the next year, it's the first and second graders that are susceptible, and that's enough to trigger a new epidemic. So that is sort of the explanation here. So, but then in Iceland, you see that it's not every other year, but it's actually every fourth year. So why is that? Well, probably because it's a smaller and isolated country. But another striking difference between these two graphs is that here in England, we see that there are reported cases all year around. Whereas in Iceland, there are no reported cases in between, or at least negligible number. So really, here it goes really extinct, whereas here it does not go extinct. But if it has gone extinct, how can it be a new outbreak then? Well, of course, there are people visiting, or there were people entering Iceland also 50 or 70 years back in time. But it was not the case that they only allowed immigrants and tourists every fourth year. So probably there came someone with measles also here, but then the susceptibility was not high enough to trigger a new outbreak. Whereas when someone arrived here, probably at the same time when school started, it was enough to start a new epidemic. So here there are enough people to keep the disease cooking all the time, whereas Iceland, the community is too small, so it goes extinct. So how can you determine what is the population size, the critical population size, above which you will have this type of behavior and below which you will have this type of behavior? That's a very interesting mathematical problem that Brian Grenfell and others have done important work in. Another epidemic is HIV. You see here, it took off in the mid-80s with a very big number of infected, and then it dropped down, and now it's endemic. And you can look at the prevalence among different risk groups and things like that. So here you can also ask a lot of questions, but I will not talk more about HIV today. So that was some real data figures. Now we go back to the world that I belong to, the modeling world. So as I said, I will mainly talk about very simple models, but have in mind that there are more advanced and realistic models. However, you should also have in mind that all models are simplifications of reality. That is sort of the essence of making models, that you want to simplify reality to keep only the essential parts of reality in your model and leave out everything else, and then you try to analyze what happens for this simplified situation. But now we go to the simplest model. So what are my assumptions? First of all, I will assume that there is no prior immunity. This is very easy to relax this assumption, but let's assume this for now. And by the way, for COVID-19, it also is reasonable to have this. Another assumption I will make is that all individuals are similar in the sense that individuals are equally susceptible and equally infectious if they get infected. That is not true for COVID-19. In particular, it seems to be the case that some people shed much more viruses than others. But we go for the simpler case, so let's assume this to be true. And we also assume that people mix uniformly, and this is definitely not true. But for the simple model, that's what we assume. So you can think of the individuals being particles in a gas drifting around in a room. That's one way to think of the model. And I am interested in the type of disease where when you recover, you become immune. Such models are often called SIR epidemic models. And that is that at first you're susceptible. If you get infected, you are infectious for a while. But after some time being infectious, you recover and you become immune. If there is no immunity, it's called an SIS model. For instance, that for chlamydia, I think SIS is considered to be the best model. There is also models, if you look at longer time spans, you have SIRS. So after some time in the recovered state, you go back to susceptible. And that is applicable, for instance, for influenza and probably for COVID-19 as well, if you look at longer time spans, but I will only look at short time spans. So then I approximate things by saying that people are immune for the time period that I'm interested in. And at least to start off, I will assume that we don't change behavior during the course of the epidemic. So these are my assumptions. And then here is a model which is by now 90 years old, Reed-Frost model. So it's a discrete time model. So you think of what happens this week, what happens next week, what happens the week thereafter. It doesn't have to be weeks, it could be days or something else, but you think in terms of generations. And we assume that we have a fixed population size of size n, and we assume this to be large, but we are looking at the time span of a few months or half a year or something like that. So we assume that it's fixed. So we neglect births and deaths. And we start with everyone being susceptible except one single individual who's infectious. That can also be generalized, probably, and at least in Sweden, I think there were several thousand people bringing in the disease. So this here is the sort of the model part. This bullet here is the model, and it's a simple model, and it says that one person is initially infected. Suppose that's me, and maybe the audience here is the rest. So maybe we have, maybe there are 300 people. I don't know. I don't see the numbers right now. So I'm infectious, and then there are 299 people that are susceptible. And then I infect, assuming that we would be in one room, let's say, I infect each of you people independently with some small probability p. Maybe p is 1%. So there are 300 people or 299 people. I infect each one with probability 1%, and then I recover. So the number of people I infect is random. Could be 1, it could be 0, it could be 5, possibly 10. If the transmission probability is 1 out of 0.01, and there are 300 people around, then most likely I will infect 3 is the average. So maybe I will probably not infect more than 10 people anyway. Suppose I infect 4 new people, and then I recover. Then the next week, these 4 people do the same thing as I did. So they infect every other person independently with probability p. Each of those 4 people do that. So viewed from a susceptible point of view, in the week 2, you have a higher probability to get infected because you can get infected from 1 of 4 people. So your probability to get infected is higher than. Maybe the effect is that in week 3, maybe 11 people got infected. Then those 11 people do the same thing, so they infect every other person with probability p. However, so you can think of that, you toss a coin to decide whether you should infect someone, where the coin is not a fair coin, but it's a coin which says infect. That side has probability 1%, and not infect has probability 99%. However, you don't have to toss coins to those that have already been infected, because they have already been infected, so they cannot be reinfected. And then maybe 11, maybe 25, maybe 38, maybe 50, but then eventually it will start dropping. So it will not go on increasing forever. It will, after a while, it will start decline, and then eventually it will stop. The reason it will stop is that we are only 300 people, so we cannot have more than 300 infections. That applies also if you consider Frankfurt or Stockholm, my hometown, which has about 2 million people. If you would run this epidemic, it would eventually stop, and the number of infected will, of course, not exceed 2 million. So it will stop. So the epidemic goes on until no new person gets infected, then it stops. And from this model has one single parameter, and that's p, but there is also a population size. The most important quantity is called the basic reproduction number. There is a sort of a general type of definition for it, but it's not, for each model it's not exactly clear what it is, but how much it equals. But the definition is the average number of new infections caused by a typical infected person during the early phase of an outbreak. And that thing is called the basic reproduction number, and the notation is R0. So typical means that it is among those people that get infected early on that you should consider how many do those people infect. And early in the outbreak is that because maybe after some time, if 30% have been infected, of course the number of new infections is then reduced. So if I consider a population of size 1,000 and the transmission probability is 0.0015, then the basic reproduction number is 1.5. So it is the transmission probability multiplied by the number of people that you could infect. And 1.5 is a common value for influenza. Whereas for COVID-19, it varies between different regions, but maybe a typical estimate for R0 is between 2 and 4. So I think in Stockholm region around 2.5, but it could be smaller and bigger. And New York City probably has 4 or something like that. So it not only depends on the disease, not only on the disease, but also on the community in which it spreads. Oh, here I see a misprint. Sorry about that. So hopefully you have understood the model. And then the question is, okay, now I understand the model. How many will get infected? Well, first of all, it's a random model. So if I was to simulate this using a simulator, but also if it took place in different villages, it would not be the same number each time. But maybe the main question is how many will get infected during this epidemic, but you could also be interested in how does it look over time. But let's start off with how many get infected at the end. So what I've done in the next 2 slides is that I have simulated an epidemic taking place in a community of 1,000 individuals, but I didn't do one simulation. I simulated 10,000 times. And the only thing I recorded from each simulation was the ultimate number of people getting infected, starting with 1. So maybe the first simulation, it was only 2 people getting infected. Maybe I infected 1 person and that person failed to infect someone else. So then I keep the number 2, and then I do another simulation, and then out of 1,000, maybe 598 people got infected. Then I keep this number 598. And then I do another simulation, maybe 630, then I keep that number 630, and I do this 10,000 times, and I have a list of outbreak sizes, and on the next slide I show a histogram where the x-axis is the number of infected, and the y-axis shows the frequency. The first slide is for R not equal to 0.8, and the second slide is for R not equal 1.5. So here is for R not equal 0.8, and we see that all simulations resulted in small outbreaks. There were 10,000 simulations, and we see that the smallest bin here has close to 9,000 simulations, and then the rest are all small. So I think no epidemic had more than 50 people infected, and the vast majority had less than 10 people getting infected. If I do the same thing, but I change this number to 1.5, it looks very different. We see that we still have some small outbreaks, but now there are also some big outbreaks. What is surprising, well, not to me anymore, but it used to be surprising, and maybe it's surprising for you, hopefully it is that there are no simulations where there were around 200 people get infected, no around 400 people, no simulations around 800 people. So they are all are concentrated close to a fraction 0 or close to a fraction which seems to be just below 60%. If I would have done the same simulation, type of simulation, but in a community of 10,000 individuals, then it would say 10,000 here, and then this would look pretty much the same, but this part would be much more peaked, so it would look more like a spike, so it would be more concentrated around values here. For those who have taken a bit of mathematics, you might think this looks a little bit like the normal distribution, and that is correct, and it's actually possible to prove that in the limit, as the population size grows to infinity, it converges to this fraction, but the fluctuations around this fraction follow a normal distribution. So that is something that mathematicians like me and others like to prove. Okay, so the main conclusion from these simulations, which can actually also be proved using mathematics, is that either very few will get infected, a fraction tending to 0, the bigger community size you look at, or else some fixed fraction tau will get infected. And this thing is only possible if the basic reproduction number is bigger than 1. Why is this bigger than 1 so magic? Well, that is quite clear, I think. If you on average infect more than 1 person in the beginning, then I think most people would understand that then it should be possible to have an outbreak. Whereas if you on average infects less than one person, then you should not expect to see a big outbreak. So now here soon there will appear some equations here, and the equations are to derive what is this number tau. So I will derive an equation which I will then solve to obtain this value tau. So tau is the fraction that get infected. Then just to remind you, then n times tau is the number of people getting infected. And if you remember, R0 was equal to P times N, which means that P is equal to R0 divided by N. So that is the transmission probability. Okay, here comes the equations. I will, don't be scared, I will explain each row. So tau is the fraction infected, then 1 minus tau is the fraction not getting infected. A fraction not getting infected, one way to interpret that is the probability not to get infected. And if you think of, if you think of the model, what is the probability not to get infected? Well, think of yourself. Suppose this model that I described to you runs through this group of 300 people. What is the probability that you don't get infected? Well, that happens if and only if every person who gets infected, when they toss their coin, they fail to infect you. So the probability to avoid infection, to not to get infected, is the probability to avoid getting infected from all those people that were infected. From each one, you have the probability 1 minus p to avoid getting infected. And you have to do it from all, so the overall probability is 1 minus p raised to the power equal to the number of people getting infected. Then I just replace p by r divided by n. So then we see we have an equation 1 minus tau is equal to 1 minus r divided by n raised to the power n times tau. Then for those of you who has taken a university course in mathematics, or maybe even a high school, advanced high school course, you know that if n is large, this expression is very close to the expression, the exponential function raised to the power r0 times tau. That follows because of this relation. So this equation will appear on the next slide. So here is the equation. 1 minus tau is equal to e to the minus r0 tau. This is an equation which determines the final size. Unfortunately, you cannot write it simpler than this, but anyway, it's very easy to solve. So for instance, if I tell you that R0 is 1.5, so if you plug in 1.5 and you ask a computer or your mobile, maybe if you have some advanced program there, to solve this numerically, the conclusion is that tau will be slightly bigger than 58%. So if R0 is equal to 1.5, it says that tau should be 58, I think it's 58.3%. And we see that this agrees very well with this solution, because this looks like the top of this mountain looks like it is slightly below 60%. So that is to me magic, that you can, with very simple mathematics, derive how many people will get infected if you tell me what R0 is. So here is the curve of the final size as a function of R0. So this 58% is obtained by, if you go up at 1.5, you read off here, you reach 58%. So we see that if R0 is 2.5, which is a reasonable value for COVID-19, then I think the answer is that around 90% will get infected. Remember that this is assuming that we do nothing, no preventive measures. And if you have a small R0, nothing will happen. I know I should take a break, so let me show the 2 more slides, then we have a short break. So the most important conclusion, I would say, that if the reproduction number is smaller than 1, we will not see a major outbreak. That is good to know if we modify the reproduction number by preventive measures or by immunity. As long as the new reproduction number is smaller than 1, we will not see a major outbreak. And if there is this disease spreading going on, as soon as the reproduction number is pushed down below 1, disease spreading will start declining. So the model results are based on 3 assumptions, which I told you earlier. There is no immunity, either natural or by vaccination. This was true for COVID-19 in the spring, but not now. So for instance, if half the community are immune, then you have a very different story. Another assumption was that we had a homogeneous community, and that's not true for COVID-19 or any other disease. So what happens if you have a more realistic model? Well, that depends on what heterogeneities are important for this particular disease. So it's hard to say anything in general, except that if you sort of compare a homogeneous model with a fixed R0 with a heterogeneous model having the same R0, then the effect is nearly always that you have a smaller outbreak in the heterogeneous situation. Maybe you have 10% fewer infected, 20% fewer infected, or maybe even 30% fewer infected. And no change in behavior, that can be brought in, but of course it makes the analytical result much harder. So here comes the same figure. The blue curve is as before. The red dashed curve is the final fraction getting infected as a function of R0, but now considering one type of heterogeneous model. I think the model I took for this to produce this curve was by assuming that half of the community were much more susceptible to the disease and the other half was much less susceptible to the disease. Having the same R0, you see that you get a smaller fraction infected. And this yellow curve is assuming that half of the community is immune prior to the outbreak. Then we see that this is very different. For instance, if you have influenza with R0 1.5, if half the community are immune, then you will have no outbreak. So immunity plays a big role. Okay, I think it's time for a break. So let's take, is 5 minutes
or maybe
suitable?
3 minutes, yeah.
Sorry?
3 minutes maybe.
Yeah, 3 minutes, 3-minute break, very good. If there is any urgent questions, you might, is there any urgent question that I should respond to now, or should we wait to the end?
For the moment, I don't see an urgent question in the chat. There might come up more during the next minute.
Yeah.
And then we will collect them for the end of the talk. Ich erinnere nochmal, dass Sie gerne auch Ihre Fragen auf Deutsch im Chat stellen können, die Sie mögen.
I didn't time it. Has there been 3 minutes or 2? Okay. You can tell me, wave to me when I should start.
Here you see a question in the chat. I don't know whether you maybe you haven't opened your chat window, but probably we also leave this question to the end. Thanks for the question already, and let's proceed now.
Okay, thank you very much. So so in my model, I said there was no preventive measures or no changing behavior, but of course that is one main reason for modeling epidemics, to understand what happens if you start inserting preventive measures. Before that, it's very instructive, I think, to sort of factorize R0 into 3 different things. So you can think of R0 as being P times C times L, where P is the transmission probability given a contact, C is the number of contacts, and L is the duration of the infectious period. Of course, what is a contact? That first of all, that depends on the type of disease you consider. But it's not, of course, one, for instance, for COVID-19, if you stand very close to someone for a very long period of time, then of course transmission is more likely than if you just talk for a few seconds and then go. So this is, of course, a simplification. But still, I think it's very instructive that there is a transmission probability, there is a rate of at which people have contacts, and then there's a duration of the infectious period. This is also good to think of when you start thinking of preventive measures, because these aim to reduce the reproduction number by either reducing P or C or L, or of course all 3 of them. So for instance, depending on what disease you think of, reducing P, for instance, for COVID-19, wearing a face mask reduces P, hand washing reduces P. If you're interested in HIV, then condom use reduces P dramatically. Reducing the number of contacts, well, quarantining people, physical distancing, avoiding public transport and public event, that's one way to reduce the number of contacts that you have. And reducing the length of your infectious period, well, one reason for doing contact, or the main reason for doing contact tracing, is to find people quickly so that they have not had time to infect others as much. So if you think of this, and then you think, let's put in a lot of preventive measures, and suppose that the combined effect of your preventive measures are such that they reduce R0 by some factor A. Then the new reproduction number, which you can call the effective reproduction number, is the old one multiplied by the remaining fraction of contacts. So we want this number now to be smaller than 1, and that is the same thing as saying that A should be larger than 1 minus 1 upon R0. So this tells you how much we have to reduce the number of contacts to get the reproduction number below 1. I will come back to this, but in a few slides ahead, but then my A will have converted into a P. So don't be confused by that. So there will be a P later on. That P will not be this thing, it will be that thing. let's go back to this graph. So it seems like from what I've said now, R0 is the most fundamental parameters, since it tells us how much we have to reduce spreading in order to stop the epidemic. So of course, then we would like to know what is R0 for this figure. Well, then there is a problem, and the problem is that we cannot say what R0 is by only observing this. Why is that? Well, the reason is that this growth rate, suppose it grows exponentially, then it grows at some rate, so the curve looks like e to the minus some, well, it wasn't there. It grows exponentially at some rate, but this rate depends on R0, but it also depends on something which is called the generation time. So what is the generation time? That's the typical time between getting infected and infecting others. So for instance, if you think of two diseases, both have R0 equal to 2. So on average, you infect 2 people. For disease 1, you do this after 2 days. And for disease 2, it takes 1 week before you infect that person. Then of course, the disease 1 will grow quicker, since you multiply by 2 every other day, whereas for the second disease, it would take 7 days to grow. So this means that there are many different combinations of R0 and generation times that produce this figure. However, if you from some other data source manage to find out what is the generation time, then you can estimate R0 from that graph that I show you. And that is how R0 is estimated, actually. And how do you obtain information about the generation time? Well, that's done using something called contact tracing. So you find infected people and you try to infer by whom they were infected, but even more so when this happened. So that is one way to get information about the generation time. A complicated way in itself, but anyway. Okay, so how about, I only talked about the final size. So what happens with an outbreak over time? Well, now I will sketch a little bit quicker, so I will not go through this. It's a slightly different model, and I will plot how the number of infectives varies over time, both assuming that R0 is equal to 3, and also assuming that we manage to push down R0 to the value 2. So there will be 2 curves, one for R0 equal to 3 and the other one for reproduction number equal to 2. From before, we know what the final size will be if you look at that graph. So when R0 is 3, 92% get infected, and when when the reproduction number is 2, 78% get infected. Of course, somewhat of a difference, but if you look at the next curve, the difference is even bigger. So this is when you do nothing. And this is if you push down the reproduction number from 3 to 2, then we see that the biggest difference is the size of the peak. So here the hospitals would be overwhelmed, whereas here they might manage. Of course, there will be still a lot of people getting infected. We see that it also takes a longer time. So at the end, there will be quite a lot of people infected, which is bad, but at least the hospitals will manage. Now to my last sort of part here, and I see that I have some at most 10 minutes left, so that's good that I don't continue more. A little bit more about prevention, but also a little bit about immunity. Earlier I showed already that the effective reproduction number, if we have preventive measures with overall effect P, remember I said A will be converted into P. Then the new reproduction number is the old one multiplied by 1 minus P. This means that the minimal preventive effect that we need to have is 1 minus 1 upon R0. Suppose that there is also some immunity in the community. Let's start by assuming that this immunity comes from vaccination and that we vaccinate individuals sort of uniformly. So let's assume that probably people will vaccinate, at least in my country, it will be that we first vaccinate the risk groups, so the elderly people and other risk groups. So that's not completely uniformly, but let's look at that situation at least. Then we have sort of two effects which bring down the reproduction number. It's both the preventive measures, just as before, but now also immunity brings down the reproduction number, because let's say that 30% have been infected, then of your contacts that you have, only 70% of those contacts will susceptible people, and those are the ones that you will infect. So this means that if there is some immunity, the minimal amount of preventive measures drops somewhat. So it used to be 1 minus 1 upon R naught, but now it is 1 minus 1 upon R naught times the susceptible fraction in the community. Now, here what I've said so far has nothing to do with my own research, but here comes a few things that has to do with what I've done during this year. And suppose instead that immunity, there is no vaccine right now, the immunity that is present in countries comes from disease spreading. So if instead this fraction, whatever it is, of immune people comes from disease spreading, then you can imagine that, so suppose maybe in Stockholm region, in the summer, I think an estimate of the immunity was 20%. We had a huge outbreak in Stockholm. We didn't put in enough preventive measures. So this summer, maybe 20% had been infected and were immune. Of those people that were immune, socially active and highly susceptible people were overrepresented. This is nothing I've showed empirically, but it seems natural to be the case. And if you have a mathematical model, you can also show that, because socially active people, they're more likely to get infected since they meet a lot of people, and also highly susceptible people are more likely to get infected. So once these people have become immune, you can think of that this immunity is somehow efficiently distributed. Sort of immunity is distributed among the socially active and among the highly susceptible, which means that once they are gone, the reproduction number when immunity comes from disease spreading is actually smaller than it is when immunity comes from vaccination. Here is a misprint. It should say DIS here. So this implies that the minimal amount of preventive measures when immunity comes from disease spreading is smaller than it would have come from vaccination. And here is a curve illustrating this. So what is this? This is the vaccination curve. So if R naught is, let's say, 2.1 and immunity is 20%, it says how much do we need to push down our contacts to avoid an outbreak. And I don't know exactly, but it looks sort of at this point, it looks like it's between green and yellow, so maybe somewhere around here. We have to push it down by slightly more than 50% maybe. And if R naught is 2.5 and we have this high immunity, so if we have vaccinated 80%, we don't have to push down transmission at all, so we have herd immunity. Here is when immunity comes from disease spreading. Then we see that it drops down quicker. So here we see that well, here's a numerical example. If R naught is 2.5 and immunity comes from vaccination, then we have to push down our contacts by 47%, whereas if immunity came from disease spreading, it would be only 29%. Finally, herd immunity. So herd immunity is what we hope to obtain by means of vaccination, because we will never be able, I think in no country, it will be possible to vaccinate 100% of the community, but the hope is that we manage to vaccinate above a certain level, which then will protect the whole population, because the reproduction number will then be below 1. So what is herd immunity? That is when the reproduction number is smaller than 1 for the situation that we have no preventive measures. That is what is called herd immunity. And if you look at the formula, it's easy to show that this level, if immunity comes from vaccination, is 1 minus 1 upon R naught. But then no vaccine is perfect. So for instance, I've heard, I'm not an expert, maybe you have heard differently, but of the vaccines that are soon to come out, we hope, the efficacy of the vaccine is of the order 90%, is at least what I have heard. Then that means that we have to vaccinate slightly more than this fraction, because not everyone will become completely immune. So for instance, this should say if R naught is 2.5 and we have vaccine efficacy 90%, then this means that we have to vaccinate at least 67% to obtain herd immunity. Whereas if the immunity came from disease spreading, but that will never happen. I think no country is aiming for a herd immunity from disease spreading, since too many people would die. But anyway, if that would have happened, the herd immunity level would actually be smaller than this value. It would be maybe between 40 and 50%, because the immunity is sort of more efficiently distributed. My final slide is to say what can we do with infectious disease modeling. So of course, pandemics is the hot subject now. And what are the questions? Well, to predict what will happen in the near future or in the distant future is something that we are working on, and many people are working on. Evaluating effects of preventive measures, that's a very important statistical aspect. And now I think a lot of countries are discussing how to, what vaccination schedules should you put in? Should you vaccinate the socially active? Should you vaccinate the risk groups, a combination of them, or what is best? But there are a lot of other problems. Endemic diseases, try to better understand the malaria, that's a vector-borne disease going between mosquitoes and humans. A lot of questions there. HIV, targeted preventive measures, treatment, how to do that. A lot of diseases going on between domestic animals. And probably in the long run, the most important problem is antibiotic resistance, trying to understand that and how you can sort of reduce resistance and still keeping the useful medication going on. The useful antibiotics should be used, but not always, but when it's important. Okay, with that, I'm finished. I almost overpassed my time, but I think I managed to keep in time.
Thank you so much.